Welcome back to the final talk today in the Yuma Theatre. This talk will be on NorNet, a Unix and open source software-based international platform for networking research. The talk will be given by Thomas Drapolz, who works as a Chief Research Engineer for the Simula Metropolitan Centre for Digital Engineering, SimulaMet, in Oslo, Norway. Thomas will endeavour to allow time for questions at the end, so please enter any questions in the tab in Venulus. Take it away, Thomas.
Thank you for the introduction. Then welcome to my presentation about our NorNet infrastructure. First, I will shortly introduce you the motivation of our work, which is around multi-homing and multipath transport. And then I come to some interesting details about our testbed infrastructure, particularly with regard to virtual machines, containers, and multi-homed networking. So what's the motivation of our work? Well, let us look first at classic internet communication in the most basic, probably example, web browsing. When you use web browsing, well, you have a PC with a web browser having an IPv4 address. This browser connects to a web server, which also has an IPv4 address. And then you have, over the TCP protocol with a three-way handshake, established a connection with three-way handshake, and you have classic client-server communication. This is the way most applications in the internet are working today, but it's a quite old way of communication. It is likely it will work this way also for many other applications in the future. But nowadays, of course, we have a bit more than such simple client-server applications. We have Internet of Things, virtualization, sensor networks, cloud computing, vehicular networks, and many other things. And these have, of course, more strict requirements on the communication. Particularly, nowadays, we not only have the IPv4 protocol, we have IPv6. And with IPv6, usually we have multiple addresses per interface and even multiple interfaces. And usually today, of course, we have IPv4, IPv6 dual stack devices. So many computers today have both IPv4 address and IPv6 address. And today, of course, we have also mobility. So probably everybody of you has a smartphone in his pocket. It's a quite convenient device. So if you are at home, you're using Wi-Fi. If you go outside, the device changes to, for example, here in Oslo, it is 5G, maybe also 4G, 3G, depending on where you are. And of course, the smartphone would even have third interface or Bluetooth. Same as classically a router. Of course, a router classically had at least two interfaces. And of course, also depending on what kind of laptop computer you have, we have also multiple interfaces like Ethernet, Wi-Fi, and maybe even mobile broadband built in. So what can you do with multiple interfaces? Well, you have the property that you are multi-homed. If you have multiple addresses, that is, you are connected to multiple networks. So particularly, you can connect to more than one internet service provider to have redundancy. So look at this user of multi-homing here. Looks not that convinced about this redundancy. What's the problem with redundancy? Well, redundancy is nice if something goes wrong. Then you still have connectivity. But if nothing goes wrong, well, if you are connected to two ISPs, each month you receive two internet bills. For example, in Australia, maybe an internet bill from Optus, another one from Telstra. Well, paying double the amount necessary is not really nice, obviously. So in 99.9 something % of the time, nothing goes wrong and you do not appreciate redundancy. So can you do something with the redundancy when everything is okay? There is the possibility to do multipath transport. if you have two ISP connections, why not just utilizing them both simultaneously? Then at least if everything is okay, usually you get higher bandwidth. This is of course nice. So with TCP, of course, with classical TCP communication, it's established between two IPv4 addresses. This does not work, but there is an extension, multipath TCP, which supports multi-homing and particularly multipath transport, and then it works. Also, if you are using the SCTP protocol, which already has built-in support for multi-homing, you can add an extension, concurrent multipath transfer for SCTP, CMT SCTP, to also have multipath transport. So in either case, you get multipath transport, so you can utilize multiple network connections simultaneously. That's a quite nice thing, and therefore it is also a topic in research and standardization. So let me shortly go into a little bit more detail about multipath transport, particularly with MPTCP or CMT SCTP. How does it work? Looking at the OSI model stack, you have the application protocol in the application layer on top of course, the kernel, which implements the transport layer, that is MPTCP or CMT SCTP, as part of the implementation of TCP or SCTP. And the application protocol communicates with the transport layer over the socket API. That is user space communicates with the kernel over this socket API. And network layer, of course, you have IPv4 as well as IPv6. So as I've said, usually you have dual stack today. So now the transport protocol can establish paths or so-called subflows over the underlying network protocols. That is subflows over IPv4 and IPv6. You can even mix subflows with IPv4 and IPv6. So you can have MPTCP connection both using IPv4 and IPv6. In the most extreme case, you can even start a connection in a pure IPv4 network, later add IPv6 addresses, and finally remove the IPv4 addresses. So you can upgrade your system from IPv4 to IPv6 without breaking connections. It's of course quite extreme case, but at least it is possible, of course. So now we have subflows, but how to put user data, payload data onto these subflows? And this decision is made by the scheduler. So far so simple, but there of course are challenges for multipath transport. And one of the challenges are particularly that paths in the network, subflows in the network, may overlap, particularly if they share the same bottleneck link somewhere in the internet. If we have multiple subflows running over the same shared bottleneck compared to a concurrent TCP connection, you get, of course, more bandwidth, which is unfair. So fairness is one challenge, and the other challenge is, of course, scheduling. When you think of subflows, maybe you think of subflows having very similar characteristics regarding bandwidth, delay, and packet loss. But of course, usually in the internet, such subflows are quite dissimilar. And then it makes sense to very carefully think about which subflows to use and which subflows to not use, particularly, to get a good performance. Performance may be bandwidth, but also some applications are latency sensitive. So maybe then it's not useful to use a subflow where you can get the highest throughput, but where you have the lowest round-trip time. So a lot of challenges, and of course research for this is necessary. But let me first introduce you how to use MPTCP. Well, it's defined as an RFC, but with some open topics still. But with MPTCP, you can make your system capable of multipath transport by extending the old TCP protocol. And a particularly nice feature of MPTCP is that it's quite backwards compatible. So on the wire communication with MPTCP look like normal TCP connections. So subflows look like regular TCP connections. That is, MPTCP will also work usually over middle boxes. That particularly means network and port address installation as well as firewalls and such. So it's quite nice because of this compatibility. So it is easy to use in existing networks. And the nice thing is there is a quite good implementation for Linux available from Université Catholique de Louvain-la-Neuve in Belgium. And also Swinburne University has some years ago started an implementation for FreeBSD. So there are 2 open source implementations available. So how can you now use it, particularly under Linux, because we are here at the Linux conference? Well, obviously you need an MPTCP capable kernel, but it's not a big deal. You can just compile one. So let me give an example. We have a computer which is connected to the internet over an Ethernet interface ETH0. And obviously we want multi-homing and multi-path transport. So we make a second connection over ETH1 to a second ISP. So does it now work multi-path transport with MPTCP? No, there's a bit missing yet. So the first problem is, of course, if we have such a setup, we have probably a default route over one of the ISPs. And of course, then the Linux routing stack uses the route which is the lowest metric, which in this case would be over ISP1. So all traffic would go over ISP1, while ISP2 would not be utilized. That's of course not what we want. We have to do something in addition. And the solution under Linux is routing rules. So we have to define separate routing tables for each ISP, ISP1 and ISP2, and then select for an outgoing packet according to the source address which routing table to use. So let me explain this in a small example. We have again our computer, and we now configure an IP address for Ethernet 0, 10.1.1.42 as /24 network. And of course, we define a default route. And this goes, of course, in the main routing table. This is as classic network configuration under Linux is. But now, as I've said, we want an additional routing table for ISP1. So we define a new table. And since the new table number 1 is empty, we have also to define routing for the local scope. And of course, then add the default route. And the same we can do for Ethernet 1, for the second ISP. In this case, we use the address 172.16.142 as again as /24 network, and create a second table, table number 2, with the local scope as well as a default route. So now we have, in addition to the main routing table, 2 additional tables, table 1 and table 2 for ISP1 and ISP2. So now missing is just a selector. So we add 2 routing rules. So if a packet is coming from the source address 10.1.1.42, we use table number 1. And if the packet is coming from 172.16.1.42, we use table number 2. Table number 1 and table number 2 are numbers. If you like, you can also use etc IP route 2 RT tables to give these tables names. For example, if you are connected to Optos and Telstra, you can name the tables Optos and Telstra. Let us look what we have configured. Now we have the routing rules, particularly the lookup for table number 1 and table number 2 according to the source address. And as I've said, these tables can also be named if it is more convenient. Usually these tables just have numbers, and internally, of course, these tables have just numbers. But there is a mapping of symbolical names to these numbers. And we have, of course, now our routing table number 1, as I've said, with the local scope as well as the default route, and the same for table number 2 with local scope and default route, in this case for ISP number 2. So, and of course, finally, we have the main routing table, the default. This is the standard routing table used for all other packets, not matching to one of our 2 new IP rules. So now our routing can work with IPv4. Question is, of course, nowadays we have IPv6. Usually, in addition to IPv4, does it work with IPv6 as well? Yes, of course. You can do the same also for IPv6. That is, get an IPv6 address for Ethernet 0. Create also the routing table number 1 for IPv6. Important to mention is, of course, IPv4 and IPv6 are different protocols. They have both their separate routing tables. So in this case, of course, this is IPv6 table number 1. And before we have configured everything for IPv4 table number 1. But otherwise, it is the same as before for IPv4. That is, we can define our 2 routing tables for IPv6 and also set IPv6 routing rules to select table number 1 or table number 2 according to the source address of an outgoing packet. So now, depending on the configuration we have made now, MPTCP, or if you have an implementation of CMT SCTP, can make use of this new routing, and MPTCP, particularly with full mesh path manager, will then of course use all paths simultaneously. This of course can be tested by booting an MPTCP enabled kernel, particularly with full mesh path manager, which has to be configured in the settings of the kernel to be compiled. And then of course you can test this with ping, and particularly tools like, for example, netperfmeter. I'll come to this tool later again. And particularly quite recommended if you learn about MPTCP and multipath transport. It's quite convenient to also observe the packet flow. And particularly this is helpful if something is not working as expected for debugging. So you can use Wireshark or command line to tshark to do this. So far, the idea of multipath transport, particularly with MPTCP. And of course, I've heard research around multipath transport is necessary. So how to do research? Well, years ago, I worked for a university in Germany at the University of Duisburg-Essen. And I and my colleague wanted to do research on multipath transport, particularly with CMT SCTP, but also with MPTCP. So we asked our sysadmin to give us hardware. We had some old PCs, some old switches, a lot of cables, and some network cards. We put everything together, and obviously did not work. The setup was quite cheap. It was in fact for free. We did not need a special budget because the old hardware was already there. But was only cheap on the paper. So particularly this hardware had sometimes issues. Particularly we observed that the network cards sometimes switched from 100 megabit per second to 10 megabit per second, just for a few milliseconds and then switch back. But the paths or subflows, which were assumed to be having very similar characteristics, particularly same bandwidth, of course became extremely dissimilar. When a card switches to 10 megabit per second, it's just 1/10 of the bandwidth on one path. So this triggered, of course, bugs in the implementation. So we did a lot of debugging of SCTP in the FreeBSD kernel. But finally, we were able to find these bugs, fix these bugs, and prove that simulations we made in advance with a simulation model were actually quite well modeling the reality we were able to create in this small testbed setup. And of course, we were already very committed to open source community. So we provided, of course, all these bug fixes back to the FreeBSD SCTP community to make the implementation in FreeBSD better. And as part of this, I wrote the mentioned tool netperf meter to do protocol performance comparisons between TCP, SCTP, UDP, and DCCP with the different parameter settings. So quite useful tool, which is also nowadays available in Debian Linux, Ubuntu Linux, and other distributions. This small setup had, of course, a lot of learning effects and new ideas around multipath transport and research on this. So the idea was, of course, then, well, we did research on internet protocols, but obviously such a testbed is an intranet setup. So let's go to the internet. So we were able to convince colleagues at 2 other universities, University of Applied Science in Burg-Steinfurt in Germany, as well as Hainan University in China, to also create testbed setups connected at each site to 2 different ISPs. So we had an intercontinental setup with 3 sites, 2 in Germany, 1 in China, and all these sites had 2 ISPs with IPv4 and mostly also IPv6. So quite interesting. We had a small internet setup, and we were able to do more evaluation work on CMT SCTP as well as MPTCP, which led, of course, to a lot of new ideas. But of course, one of these ideas was obviously we had a 3-site setup, but still quite small compared to the big internet. Can we make this bigger? And of course, yes, we can. So also the Simula Research Laboratory in Norway had ideas around creating a testbed setup for multi-home systems. So they published a job opening. I applied. And a few weeks later, I was moving to Norway to create the NorNet testbed consisting of 2 parts. NorNet Core is the landline part. This is what I, in this talk today, will introduce in a bit more detail, which connects such server setups as in the figure at different sites with up to 4 ISPs. And we had 21 locations with 11 in Norway and 10 abroad. And of course, nowadays, we not only have landline connectivity, particularly we have mobile connectivity. So NorNet consists also of a large part called NorNet Edge, which distributes these embedded systems all over Norway, around 200 locations, to do measurements of the performance of the Norwegian mobile networks. We'll not go into too much detail about NorNet Edge here because of time constraints. Instead, I will present you some more details about NorNet Core. And as I've mentioned, we have in total had in 2016 21 sites, 11 in Norway and 10 abroad. Today it's a little bit fewer sites abroad, but still 11 in Norway with up to 4 ISPs. And wherever we were able to get IPv6, these ISP connections also in addition to IPv4 have IPv6 support. And particularly with such an infrastructure, often we on own sites, you can get a lot of details about the internet connectivity. Now we have developed the tool HyperConTracer to continuously measure the routes by traceroute measurements inside this infrastructure. And this is a view over 1 month from July 2016. Particularly interesting about such intercontinental setups is, of course, that these routes in the internet frequently change, particularly between, for example, Europe and China. So particularly also depending on the combinations of ISP locally and remotely, you can see that some of the connections go westwards over United States, while other connections go eastwards over Russia or Dubai and other locations to East Asia. So quite interesting. And particularly, of course, as mentioned, we have quite interesting sites, and particularly when it comes to remote systems for our NorNet setups. Well, our servers can be really remote. We have a site in the city of Longyearbyen on the island of Spitsbergen in Norway. It's at 78.2 degrees north. So around 1,200 kilometers just from the North Pole, probably one of the northernmost places you can place servers. So we deployed the site setup on a nice spring day. It was just minus 30 degrees and sun was shining. So you can imagine how it looks like in really winterly conditions with a lot of storm. And cold temperatures, they are also not the only challenge. The other challenges are wild ice bears roaming around in this area. So obviously, if you think about such a site, if something goes wrong with the site and somebody has to go to the site, and this is the way of transport in Longyearbyen, it's a snowmobile, so there are no regular roads, so you have to drive a snowmobile. So areas where there are wild ice bears roaming around. So it's a challenge. So obviously we have to think about what can we do when something goes wrong. And things can go wrong because we have experimental systems and there's Murphy's Law. Anything that can go wrong will go wrong. So how can we avoid that experimental software brings down our infrastructure so that somebody has to go to the remote site and do some maintenance work? Well, the idea was then to use virtualization. So actually, our server setup consists of a very lightweight setup of Ubuntu Server LTS. LTS is the long-term support version of Ubuntu with 5-year support. So therefore, it's quite stable and quite well maintained. And everything else goes into kernel-based virtual machines, KVM. That is particularly the routing software goes into a dedicated virtual machine exclusively running on one of the servers, and all research software goes into virtual machines on the other machines. So that is, if something goes wrong, it's possible to log into the host machine and do some repair work. That is how does such a physical machine look like. As I've said, it's Ubuntu Server LTS. It's one customization, which is interesting to mention. We decided to use RiserFS version 3 instead of ext4 because of its robustness. RiserFS actually has a bit bad image because it's named after the author of this file system who killed his ex-wife. But actually his file system is quite good. So it never killed our data. And particularly it never needed manually file system checks at boot time, which are quite important. Which is a quite important property because if the remote machine wants a manual file system check on the console, it's quite annoying. We have to the browser people at the remote site do this for us, but not with RiserFS. So therefore, we started with RiserFS. Nowadays, after unfortunately RiserFS has been removed from the installer of Ubuntu, for new installations we use BTRFS, which became also much more stable in the last few years. And as I've said, we are using KVM, kernel-based virtual machines. Originally, we used VirtualBox, but this was then requiring, VirtualBox is open source itself. The VNC implementation is not, so it required a blob from Oracle to be installed. And we were not really satisfied with the stability of this. So we decided then to move as soon as possible to KVM, which is quite stable. This is the physical machine setup. Now coming to the router setup, so-called tunnel box. I'll come to this name later. Well, the tunnel box connects the machine to all the ISPs of a site, particularly having one IPv4 and, if available, one IPv6 address per site and ISP. Of course, these addresses are public addresses, but for research experiments, of course, for a researcher, nice to have his own IP addresses. Of course, if you ask somebody for a /24 public IPv4 address space, that's of course not possible, because IPv4 address space is exhausted since several years. So IPv4 addresses are quite scarce resource. So what we had to do was then to think about establishing tunnels between the sites over GRE for IPv4 or IPv6 in IPv6, so that we can apply our own systematic addressing scheme with private IPv4 addresses. And of course, then we can give each site a /24 with 10.provider.id.site.id.node.id. And for IPv6, of course, we have our own prefix and can give for each provider and site a full /64. With this, of course, we can then allow researchers to use own addresses for all the research experiments, which is quite nice feature. And particularly, of course, with these private addresses, direct communication between all the sites is possible. And for external connectivity, we had to decide, well, we can, of course, route external traffic at the tunnel box of a remote site directly. But this causes, of course, issues for many hosts. Because, for example, we have sites in Germany, and they have very strange regulations according to copyright and file download and such. So, in fact, to convince somebody to host a site in Germany, there is no chance if there is a possibility that people can do arbitrary downloads from the internet. So, therefore, we route all external traffic over similar site. So, in fact, then if somebody downloads something from a remote site, even mistakenly, for example, do a video download for testing, then it goes out over a Simulus address in Norway. And of course, in Norway, we have much more relaxed regulations when it comes to copyright and such. So therefore, this was quite important decision, which was necessary, unfortunately, due to such regulations in some countries, particularly Germany. Well, now we have the router for doing the routing, but of course, although we have quite systematic IP addressing scheme, it's sometimes difficult to remember all these IP addresses. We have also made our own DNS setup using a bind DNS server. So we can name our devices with provider and site names. So to have the possibility to do lookup of the IP addresses, and particularly, of course, reverse lookups of IP addresses to symbolic names. And of course, since countries like Norway or Germany have extended set of characters, we have, of course, also support for Punicode, works even for the Chinese side with Chinese names. So this is one convenience, and the other convenience is, of course, inside the DNS infrastructure we can also put the SSH key fingerprints as well as geolocation information as SSHFP and LOC resource records. And since we route external traffic over Simula, makes, of course, sense for package updates to be cached by a squid proxy. So also on the tunnel box, therefore, there is a squid proxy running to cache particularly Linux installation packages, so that if multiple virtual machines at a remote site have to download the same package, that not all these packages have to be downloaded via Simula. This is the router, and now let's introduce the research node. So usually research nodes by default are managed as part of a software called PlanetLab Central. This is the same software PlanetLab uses, just with a slight modification to have, of course, an MPTCP capable kernel, and as well as a special configuration for multi-homed routing. I will show an example later. This is currently based still on Fedora Core 25, which is a bit out of date now. This soon requires an update, so we are working currently on this to do some enhancements and updates of the software. But what this Planet App Central software does is in fact to provide containers, LXC containers, for research experiments, which have in fact just this Fedora Core Linux installation, but this Planet App software is actually quite smart. Not for each research experiment there is a requirement to install a complete Fedora core system, but in fact it just works like having a base installation on a BTRFS file system, which is then cloned, so that is just doing copy on write. So it's quite efficient when it comes to storage space, and also, since it's using containers, also quite efficient for memory. So it's just around 2.5 gigabytes of memory. It's possible to host multiple research containers. Of course, besides Planet App Central software, it's also possible to instantiate custom virtual machines, for example, for machines running FreeBSD or more up-to-date Ubuntu system or systems with own kernels, if this is necessary for your research experiment. But usually for many experiments already possible to run this Planet App Central based software. What is our physical nodes look like that they run these Planet App Central based nodes as KVM virtual machines, and inside these KVM virtual machines are running LXC containers instantiating so-called slivers. This is the name of a container in the terminology of the Planet App Central software. So we can run multiple of these PLC nodes as separate virtual machines on the same physical host, in addition to possibly further KVM-based virtual machines, for example, with special Ubuntu installations or FreeBSD installations. So that is when the usual user logs into one of these slivers. Then what the user sees, of course, is that the machine has multiple IP addresses, one for each ISP. But this is a sliver that is an LXC container at Hainan University, which has two ISPs. One is CERNET and one ISP is China Unicom. So the machine therefore has two IPv4 addresses and two IPv6 addresses. So that is, in total, this machine has 4 different IP addresses. So outgoing, these 4 different IP addresses can be used then, of course, particularly with MPTCP. And as I've said, the kernel of the host machine is running MPTCP. And since this is a container, of course, the user of this container has the possibility to run MPTCP as well. And particularly with the tool netperf meter, it's possible for the researcher to turn on and off MPTCP, or even have concurrent TCP and MPTCP connections to do some comparisons for the performance of MPTCP and different settings with MPTCP. And also particularly what is installed in these containers as well is a tool system info, which displays this information on login, particularly information about SSH key fingerprints and the IP addresses. And of course, these containers have sudo permissions. That is, the user of these containers has the possibility to just with sudo install custom software as well for running research experiments. So this concludes my presentation on NorNet Core. That is, I've shown you the ideas of multi-homing and multipath transfer, and of course introduced you the NorNet testbed infrastructure. And particularly to mention is, of course, NorNet Core is an open testbed, just like Planet Lab. So if you are interested in doing research in NorNet, of course, it's possible to join NorNet Core and also use this testbed infrastructure. So quite interesting thing to do, particularly if you are doing research on networks, particularly with multi-homing, but also around routing and such. And currently we are thinking about the future of NorNet, particularly we want to obtain more funding, new funding particularly, to extend the scope of NorNet Core beyond this basic idea of multipath transport, but particularly in the areas of network function virtualization and software-defined networking, but also around cloud computing and applications. Particularly, this NorNet Core infrastructure can also be seen as a distributed multi-cloud system with several sites. So it's quite interesting for cloud computing applications as well. And particularly if you are interested in more details about NorNet, you can find a lot of information about NorNet on the NorNet website www.ntb.no. And particularly we're also very committed to open source software development. So a lot of software coming out of NorNet is of course available in different web pages and particularly in a lot of GitHub and Bitbucket repositories. So just have a look. Most of the software is licensed under GPL. And of course, we are a research testbed, so we have of course also a lot of research literature with results out of experiments in NorNet Core available. You can find all these papers also on the NorNet web server under the publication section. So now we are almost over time, but we still have a few moments for questions. So thank you for your attention. And now we have probably around 2 minutes for questions left.
Okay, thank you, Thomas. I'm here now to give you the questions. There is currently one question available, and that is, where is the Planet Lab central distro available?
It's on our NorNet web server. There you can find the links to all the GitHub repositories. So the original upstream software is available, of course, from Planet Lab, and our changes are in separate Git repositories, but they are linked on our NorNet web server. Okay. And the questions, of course, if you do not find it, you can just write me an email. Then I can send you the links.
Thank you. That's all we have in terms of questions. Would you like to wrap up at that point, or do you have something else to add?
Particularly if you later have questions, just write me an email, and also will be available at the conference in chat rooms.
Excellent. Okay, thank you, Thomas.
Thank you. Have a nice day. And enjoy the rest of the conference.